Well, hello, welcome to Build. My name is Steve Wright. I'm a senior program manager with Microsoft. I've been here about 20 years now, and for most of that time I've worked on display technologies and input technologies. Over the last 3 years in particular, I've spent a lot of time looking at high DPI displays and how we can make Windows work better with those devices. And so here, today, I'm going to talk about Windows 10 display scaling, what that is, and why it's important to you. So what it is, just very briefly, and you'll hear a lot more about this in the course of the discussion, is it's a platform technology. It's baked into our low-level frameworks and is available to all applications. And why it matters to you is that this technology takes a great deal of burden off of you as individual developers. We're going to spend a lot of time explaining how that works, why it works the way it does, and then what's left over for you guys to do. So I'm going to give you kind of a quick rundown agenda of what the talk's going to look like. Just like hardware displays and form factors are an evolving technology, scaling in Windows has also been evolving over the last several years. And there's some really new stuff in Windows 10 that it's important for you to learn about. So I will be spending some time talking about that and how we have overhauled the scaling system for Windows 10. In a nutshell, and to forecast what I'm going to be saying later, we've provided a scaling system that now works the same for all applications in Windows, and which works the same across all displays and mobile and desktop SKUs as well. So a great deal of uniformity and simplicity. And as a result of that work, the Windows platform now takes a large amount of work off of the back of you as developers. It frees you up to focus on something that you'll hear talked about a lot at this conference today that are called effective pixels and effective resolution and adaptive scaling and layout. So we're going to define exactly what these mean in just a moment, but they're very important subjects you'll find discussed here, and I'll provide some pointers to that later on. But the purpose of this talk is to kind of lay the groundwork for that by taking the hood off of the scaling system, showing you how it works, why we built it the way we did, and we can kind of call that Display Scaling 101. So some of this may be familiar, but some parts of it may be new. We'll start there, and then we'll go into the changes for Windows 10. And from there, we'll kind of go back into the developer story for display scaling in Windows 10. So, just to motivate the entire discussion in more concrete terms, why scaling is important to you is that your application is going to be running on a lot of diverse screens. I mean, a huge number of them. And they're diverse in many different ways. Different sizes, different resolutions, densities, and viewing distances. For example, here are two screens with very different sizes. The little one below could be as small as a 4-inch phone. The one above could be as large as an 84-inch Surface Pro Hub, or even larger screens in the future. That's a 20-to-1 ratio in size. In terms of resolution, you could be looking at a similar phone with very low resolution and up to like a 4K or even a 5K monitor. And we know that people are starting to think about 8K devices coming soon. So there you're looking at, what, a 6-to-1 ratio right now and capable of growing in the future. Different densities. Here things are kind of oddly inverted. That Surface Hub device actually has a very low density, about 50 dpi. But a phone, a high-end phone, might have as high as 500 dpi today. And maybe that could be growing as well. So there's a 10-to-1 range. And finally, those same two devices could be viewed at very different viewing distances. 18 inches for a handheld device, 120 inches or more for a wall-mounted unit. So there's another 6-to-1 ratio. This is an insane diversity, if you think about it from a developer's perspective. There's no way in the world that you want to have to target each one of these different gamuts and the entire range of each one. So, we provided DPI scaling, or density scaling, or display scaling, and it abstracts much of this complexity. For example, one thing that you'll get out of it is something that we call device-independent or effective pixels. And these are common across all the different devices. That means that if you develop to those, huge promise, your customers will get content that looks reasonably the same on all devices. And there's even a benefit here for the hardware developers in that there's an extensible scaling solution that will support them as they build bigger or more dense displays in the future. So what does that leave for you? Well, one really big message, I've already referred to this once, and again I'll point to some other talks on this later, is it lets you start thinking about doing your layout in these effective resolutions. A much simpler story. The other thing that I want to talk about in this talk is that you need to design your bitmap assets so that you can support these different scale factors. And we'll see why you have to do that. So it's time for what I call Scaling 101. We have to define some of these terms. I've been throwing around terms like effective resolution and pixels and density and viewing distance. Let's take a look at what they actually are. So screen resolution, everybody sees this when they look at specs for devices on the web. It's how many physical pixels across or high a device is. And you may talk about a 4K monitor, 3840 by 2160, or a low-end phone, which might be 480 by 800. That's the screen resolution. Usually people talk about the size, not with the 2 dimensions, but just with the diagonal. That's kind of common coming from the video industry, and we all use that. So here's a diagonal of a 5-inch phone. The density is how many pixels actually fit into an inch. And in the example here, we have 160 dpi in an inch. That would be kind of typical for a low-end phone. It'd be higher than you would find on a desktop. And so that leads us to the physical pixel. That's the smallest unit on the screen, the smallest little thing that can be lit up at a time. And we have here 3 different screens. Some of them are much denser than others, and they have smaller real physical pixels. This is exactly the kind of chaos we're trying to take you away from. And we can do that by providing something we call an effective pixel, which is device independent. And you can see in this picture that it's the same size on the screen. Now, one thing that happens along with that is that we go from the physical resolution that we already talked about, the screen resolution, which ranges from a 480 by 854 here all the way up to a 1080p. And when we take into account the scaling and the effective pixels, then those resolutions become expressed as effective resolutions. And you notice they're much more in a consistent range, and they kind of grow as you go from a 4-inch to a 5-inch to a 6-inch phone in a kind of a rational way that doesn't depend upon the density of the pixels anymore. I think you can begin to see from this why this is going to be a really great thing for you when you're doing your design and layout work. So the effective resolution is just the size of the screen in effective pixels, and display scaling is just that underlying technology that maps the effective pixels into the physical pixels. All right, so that's actually kind of a lot of overhead in order to try to make all the content look about the same. Why is content size that important? Let's talk about that. So there's a cardinal sin when you're making presentations that you never present an eye chart. But I wanted to actually present an eye chart here, and it's a real eye chart, the kind you would see in your optician's office. And it's perfect for this because it explains exactly why content size is so important. You can look at this, and everybody can easily read the content at the top of the screen, that big E, the FP, the TOZ, and so forth. But by the time you get down to that bottom line, even without my glasses, I'm having trouble with it. So this is an eye chart, and it basically shows that content size is very important. If content gets too small, your users, your customers, our customers can't read it, can't interact with it. So just as the optician gives you this chart and then provides you with lenses that basically normalize the acuity of your eyes to what we think kind of the norm is for most people, one thing we do in Windows is we use DPI scaling to normalize the content so that it looks the right size for people as well. Now the question is, how big? We could start at the top of the chart. It's highly readable. You only get 1 word at a time. It could slow you down a little bit. So clearly you want something a little bit smaller. Well, we still don't even have a complete sentence. Now we've got a complete sentence, but things are starting to get a little bit hard to read. So we've gained in terms of context, but we've lost in terms of size, and this can go absolutely crazy if we keep going in smaller and smaller sizes. So in that gamut, there's a kind of a trade-off between a size that's easy to read and a size that permits you to have enough content so that you can actually read a conceptual block of information and understand it. How do we find the right size between the one extreme and the other? Where's the right place to trade off? And here we have great data from reading. People have been studying reading speed and font sizes for a long time. And if you take their data and you graph it, you can see that there are kind of 2 different regimes. There's an area above a certain type size in which basically reading speed is very high and fairly consistent level. Clearly you don't buy anything by increasing the size of the text above that point. But on the other side of that, there's a regime where reading speed falls off pretty quickly as you make type get smaller and smaller. And so, for example, a person with 20/20 vision can make out roughly 3-point text from 16 inches away. But that would be very slowly. On this chart, that comes down to about 40 words per minute instead of the 400 or so that should be capable to you at a good reading size. So you're at about 10% of your reading speed. And usually that inflection point where we pass from one regime into the other is about 3 times that minimum level of acuity. So what happens if we err too much on the size of small? You'll get a lot more content, but people will tend to squint. They will keep their eyes open These are just kind of involuntary responses to dealing with small things. And so your eyes dry out, and you start having fatigue, headaches. So small text not only slows you down, but it also increases your visual fatigue. And both of these are issues for both the comfort and the productivity of our customers. So we want to keep it well out of that range. Now, this is an important point here. Not everybody is the same. Individual users have to be in control of things. For one thing, as we age, that curve traditionally drifts a little bit towards the right. We begin to lose the ability to read as quickly, even with lenses, just because our eyes are aging. And even in a given age group, there are different kinds of reading that people do. Somebody who's just reading fiction probably is going for speed. A coder, however, speed is not so important. It's really more important for somebody who's doing code development to get a lot of context on the screen. And he's not going to be reading code at 400 words a minute. He's going to be studying small pieces of it. So for somebody like that, actually getting down on the other side of the curve where you want to move very slowly could be an appropriate thing. So we have to provide a way for users to control this. Now, I've said several times things about viewing distance. I mentioned 16 inches and different distances and so on. Why is viewing distance important? Well, this is really critical to our platform. Nobody else seems to take this into account the way we tried to do. Clearly, the optimal size we want to put on a screen is going to depend upon how far away that screen is from you. You remember the eye chart. If you were in the optician's office and he asked you to read the line and you could just say, "Excuse me a minute, doctor, let me go check." And you stood up and walked up to it and said, "I can read the bottom line, no problem." Clearly, you're getting around the whole point of his test. And for similar reasons, when we have screens at a great distance, we need to make things bigger. We have screens that are very close. We need to make them smaller. So scaling depends upon viewing distance. As we said earlier, we have a range of about 18 to 120 inches in our devices just today, a 6-to-1 range. Clearly, that's too big a range not to pay some attention to when we do our scaling. So our goal is that the content will be scaled larger on more distant screens, large and less so on closer screens, so that it appears at roughly the same size as in this picture. Now, you're going to say, yes, but users still have to be able to control this because perhaps I, as a phone user, tend to hold my phone farther away, or as a desktop user, maybe I tend to lean in a little bit closer to my screen. And that's absolutely true. There's a lot of individual variation here. So our solution has to also provide the way for the individual user to change the scaling on each display. So here are 3 different screens with the same content on them, and you can see that the content is actually using different scaling factors, 200, 150, and 100, and the content does not look at the same size. But that's because these devices are meant to be seen at different viewing distances. If you take that into account, you can see they're starting to look like the same size, and when you actually get at that vantage point, you can see visually the content subtends the same angle for everybody. So that's what we're going for with this. Now let me come back to my presentation. So we talked about viewing distance and why that matters. It should be pretty obvious that display density has much the same impact. If we always rendered a particular font glyph, like the small I here, to a fixed number of pixels, then on devices with smaller pixels, the content gets smaller. And here over like roughly a 5-to-1 ratio, if it's important that content be a certain size, then we have to do something to adjust for it as the number of pixels gets greater. And so what we really want to see is a benefit that comes out of these higher DPI screens where we keep the same size, but as the number of pixels increases, we can use more pixels to render the shape more and more precisely. And this actually becomes easier to read as the density goes up. Now, in this case, going past about maybe 200 DPI or so is probably just a nice to have. But in other scripts, the problems can be far more severe. Here we have a character which has, I think I counted on the order of 23 or 24 white and black horizontal bands just to define it. At 11 points on a Windows desktop machine at 96 DPI, you only have 15 pixels to work with vertically, and there's just no way you can bring out that level of detail. Even at 300 DPI, you can see, if you look very closely, that some of the horizontal lines are not defined quite as crisply as others are. And this just has to do with still not, even at 300 DPI, having enough resolution to actually describe this glyph perfectly. So we think there's actually quite a bit of headroom for DPI, particularly when dealing with these kinds of Far Eastern fonts and scripts. So This is a good time to step back and just take a look mathematically how we take all this into account. We've said we need to take into account the density, we need to take into account the viewing distance, and it's really not very complicated. First, we have to find out how many pixels there are per inch. One way to do that would just be to take the resolution divided by the width. But since most people express the size of the device in terms of the diagonal, we have to come up with an approximate diagonal representation of the number of pixels, and we can just do that using the Pythagorean theorem. So we take the resolution in the x direction and the y direction that came off of that first screenshot several slides back. We square them, we add them, we take the square root, and then we divide that by the size. And that gives the density, and that comes out in dots per inch, because the resolution in x and resolution in y are both dots, and we end up dividing that by a size. So this all comes from the screen geometry. We can get that information as soon as we see a display plugged in. Now from that, we extract what we call the scale factor. And basically, it scales just like the density, but it also scales like the viewing distance. So our kind of gold standard or our reference machine is a classic Windows box running at 96 dpi, sitting on a desktop, roughly 28 inches away. So based on that, if we know the density and it's not 96, and we know the viewing distance and it's not 28, we can just take those ratios and then scale that 100% by that. So 100% is that reference device, and other devices then get larger and larger values. We don't really see very many devices that fall below that. Even the Surface Hub with the 50 dots per inch, because it's being seen at such a large viewing distance, ends up having a 200% scale factor. So you can see we factored the density and the viewing distance in, and then we can go to the effective resolution, which is just the screen resolution in x and y scaled down by the scale factor. So once again, the screen geometry comes in and then the scale factor from the previous calculation. So this is how we do the work to figure out what the scale factor should be, except this is just the first step. The problem at this point is we've come up with a number which is going to be different for every display. And there are hundreds of different displays out there. They don't all fall on top of each other. You would end up, as a developer, seeing dozens, at least, of different scale factors that you'd be asked to support, and dozens of different effective resolutions. We haven't really solved the problem for you if we just give it to you this way. We've taken away some of the degrees of freedom, but we've still given you an enormous gamut of stuff to try to consider. So, at the end of this calculation, we then snap these results to what we call plateaus or buckets, or frankly, we just call them scale factors. And even though there might be hundreds of different percentage values between 100 and 400%, we're only going to have a few buckets in there, and everybody falls into one bucket or another. It's a rounding kind of thing. So we take that computed scale factor from the previous slide, and we just round it to one of the supported scale factors. We can do that up or down. We have thresholds in place where we make the decision to go either up or down. And then there's one last thing. We also guarantee you as developers a certain minimum resolution that you, for example, on a mobile device, we say your resolution will never be below 320 by 480. So in order to enforce that, we have to look at the result of this computed scale factor after we bucket it. We look at it and we say, okay, what is the effective resolution? And if it's less than the guarantee, then we say, oh, we got to lower the scale factor and go for a larger effective resolution. So in pseudocode, we basically would do a little while loop. You can think of this as iterating, that we'll just keep iterating and going to lower and lower scale factors until we get to an effective resolution which is actually greater than or equal to the minimum guarantee. And those are the values we now support for Windows 10. This is new. 800 by 600 is a step down from what we used to support for desktop, but we've found that this is really important for a number of small tablets in the 7 and 8 inch range that want to support desktop. This gives a better experience. And the phones also, we're seeing on some of the smaller phones, it's important to have a smaller resolution there than we had in the past as well. So the end of this means that the scale factor you actually see on the device is not going to be exactly what the physical geometry would lead you to. There will be some rounding differences, and this variation can be a small amount up or down. The good news is, if we have enough buckets, and each bucket is not too big, then the amount of variation you can have within that bucket is constrained. And so the size doesn't get too far out of whack, and that's really been an important goal. So, how does this really work? I've been talking a lot. Well, here's an example. Here are some devices. These are actually some of the same devices I showed at the very beginning of the talk. You can see all the diversity in terms of their size, their density, their resolution. But when we add scaling to the picture, this is what you see. First, note that the visual size of the effective pixel, as measured in a kind of degrees, is amazingly close. We've got it within basically a 10% up or down range at most. And the effective resolutions are now in a much tighter gamut than the physical resolutions are. And then we have various scale factors that we've picked out of our set of plateaus. So at the end of the scaling process, we can give you an effective resolution that you can use in layout. We have the scale factor that we usually give to the app framework, and it does the magic scaling for you. And you end up being able to code your design to these effective pixels and be very confident that the experience you're going to provide is going to look reasonably the same across all these devices and will work well for your customers. Now, this is just scaling 101. We could say this about almost about any of our releases. What have we done differently in Windows 10? Well, there's one big, huge thing. We've unified our scale factors for all classes of applications in the platform. We've come to a fairly simple set of scale factors: 100%, 125, 150, 200, 250, 300, and 400. And this replaces quite a bit of complexity we've had in the past. So there are some compat exemptions. There are existing apps out there for 8.1 and Windows Phone Blue that expect other scale factors, and we have those shimmed in quirks so that they will actually run as they used to on a particular device. But moving forward, with all the universal apps, we expect people to be coding to these scale factors. So why those? There's a number of reasons. For one thing, they align really well with some other app platforms that are out there, in particular Android and iOS. We thought this was really helpful if you were trying to target multiple platforms with a particular application. At least we should make it possible for you to use your assets back and forth across the different ones. And so if you've already supported Android, you're already supporting most of ours. If you're supporting iOS, even just 100 and 200, you've got a really good start on what you need to do for Windows. And I will say, and we'll talk about this in more detail, you don't actually have to support all of these. In fact, I put in boldface the ones that we think are most important to support, and we think that if that's all you support, you'll have a pretty good story. So there's the industry alignment. There's other issues. These are relatively granular. They're certainly more granular than the competition. We actually think this is a good thing, especially if you don't have to provide assets at these intermediate values. Our ability to set the platform at them means the content size can be more tightly contained. Remember what I said earlier about keeping the buckets small and close together. If you look at the distance between 200 and 300, for example, if you had a device that fell right in, it should be right at 250, then it's either going to be, 20% too small or almost 20% too big. Those would be the only options if we didn't have a 250. We have the same issue down here for the 125 between the 100 and the 150. It's even conceivable in the future that we might decide that we would need to have some additional scale factors in here that we would add at some point in the future. Again, it's with the goal of keeping the content size remarkably consistent for all your users, and also with the goal for you as developers that you still only have to support a handful of scale factors. So we think this granularity is a really good thing. Another big change, in the past, I think all of our scale factor systems topped out at around 250, but we know 4K devices are coming, and we know that we're going to need 400% scaling within the next couple of years for some of those devices. So we've built that all the way out to 400. And of course, we can see how that would extend forward in the future when people start throwing 8K devices at us. So, what does this mean for you as a developer? Well, I always like to draw what I call a pyramid chart. We provide something in the platform that's kind of a base for everything, and we've already talked about that, so I'm not going to go into it anymore. We give you this. We come up with a scale factor and an effective resolution. We give that to you. Then you as a developer fall into one of several classes, and this is where the application pyramid. Most developers just fall into the bottom area. These are things that every application should be doing. We call this a mainstream app, for example. One thing is use the effective resolution in your design and layout. This is the whole subject that I said before we've got multiple talks on elsewhere, and again, I'll provide pointers on that later. But for purposes of this talk, we want to talk about providing these assets for, as I've already said, some of the scale factors. Now, where do you go beyond that? Well, there are a few apps that have very exacting visuals. They may want to provide some more of the scale factors themselves, rather than relying upon the system to do the scaling for them. And then finally, there are a few applications that actually have to know a little bit about physical pixels. I don't want to go into that in any detail here, but just to give you an example, if you had an application that had to put a ruler on the screen, for example, so that you could measure things, you would need to actually know how big the physical pixels were in order to know how far apart to space the lines on the ruler. There are APIs for that. We had those APIs in Windows 8.1. They still exist. You can still use them. I don't need to spend any more time talking about them now. But this is a relatively small case. This is the big case. A few developers will have higher quality needs around their assets, or they'll have more detailed assets. They can go with this. And then, again, for just a small handful of scenarios, you might need those APIs. So let's talk about those bitmap assets. At this point, you may be remembering, if you had attended some of the previous bills, that we had similar issues when we were talking about Windows Phone apps in Windows Phone Blue and in Store apps. And there were a lot of questions that come up around bitmap assets. We have a lot of scale factors. How can you support them all? Which scale factors should you support directly? Why not just support all of them? What happens if the platform has to scale these to different displays and you haven't provided them? How can you control which assets go to which devices and displays? These are all really important questions, and fortunately the answer is it's a very similar story to what we had before. And so what I want to go now is go into it in detail and show how it applies to the Windows 10 scale factors. So let's talk about bitmap assets. If you only provide, say, a 100% asset, and I have to tell you, about half of you out there are doing that today. Our telemetry says only 56% of our developers are supplying more than a 100% asset. What that means is that at runtime on any other device with any other scale factor, we will do our best to stretch that asset to fit, and we'll give you the right size because that's our number one goal. But the quality of the scaling may be pretty poor. It's not too surprising. This is like a 32 by 32, so you've only got 1,024 bits of information. You're trying to stretch that out to 128 by 128. You don't have the information to provide a nice crisp image. You just don't. And so this is the best that can be done within the system. Now, I'll give you a caveat that if you actually displayed this on a very high density screen, the blurriness would not be as bad as this because the pixels that are blurry are going to be really small. But you can see the difference between this and this on two screens side by side. And what I'm telling you is that about half of you out there are basically letting your customers live with this kind of experience instead of a crisper one. Okay, scaling up is not really good. That makes sense. We all understand that theoretically. What about scaling down? Well, it looks beautiful. If you do the same experiment, but you start with the 400% and scale it down, it's much better at every stage. If you get these guys right next to each other, you can sometimes see that this is a little bit better, depending on the art. But in general, it's a great story. So why don't you just do that? Well, the answer is we don't want you to just provide big assets. And there's a good reason for that. Your apps may be running on very low-end devices that don't have room for a lot of big assets. Don't forget that in memory, the size of the asset grows as the square of the scale factor. So if you're doing a 100 versus a 1400, you're talking about a 16:1 ratio. Now, in disk footprint, it may not be that bad because at least this icon content tends to compress pretty well. You can see you only got about a 4:1 ratio. But in order to render it on the screen, you are going to have to expand it out in memory. And so this is starting to eat up a lot of memory at runtime. And this is just one very small asset. What if you had like 100 of them? And what if you needed larger ones? You could end up easily with 10 megabytes of memory footprint at runtime, which would be fine on a very high-end device, like a desktop machine or even a high-end phone that's got a lot of RAM. But you don't want to be burdening low-end customers that have 500 megabyte phones with 10 megabytes of data that they really don't need because their device is probably only running at 100%. So we have a solution for that. The first step is you do need to provide more than one asset. You need the 400 for the high-end devices, and you need 100 for the low-end. And we've found out in practice that having one in the middle is a good idea too. But by itself, this is still not enough because you're giving people 100 and a 200 or 400 all the time. So the other part of it is use asset packages. And this is a technology that means that your users only download the scale factors they actually need on their devices. That's not a new technology. But right now, our telemetry says that only about 19% of our developers are using this. So this is a really important thing we want people to take home and study and learn how to use properly. So let's talk a little bit about the runtime and how that manages asset selection and where these asset packs fall into it. So there's a technology called MRT, Modern Resource Technology, I think it's what it stands for. And it's basically a technology that manages assets of various kinds, strings, bitmaps, that kind of thing. And as a selection mechanism, it's driven by resource naming. So in the case of scaling, if you had an asset named friendly name.ping, you would just generate versions named friendly name scale-100, scale-200, and so forth, and just name them that way. And that is enough for the Windows runtime to pick them out and treat them as different variants, different scale factors for the same asset. And in your code, you just use the friendly name.ping. You don't have to address the scale factor at all. And then at runtime, the runtime will pick the best available version. It'll look in your assets folder and it'll see, oh, I see a 1 and a 2 and a 400, and I'm running at, say, 150%. I will pick the 200, and that was the best one that's available, and then I will, if I need to, I'll map scale it down to fit, and the result should be pretty good. Well, what does best actually mean here? Well, I don't want to go into the exact heuristics. The heuristics do favor downscaling over upscaling, as they should, and they do favor being closer over farther. The upshot is that if you actually specify the 100 and the 200 and the 400, this is what will happen at runtime. We'll use the 400 to downscale to 250, and maybe up in the future. We'll use the 200 to downscale to 125, and we'll use the 100 for 100. And the results of that look very good. Okay, so you've generated your 100 and your 200 and your 400. What is this asset pack thing? This is what's really important. An asset pack is just a way of building your application in Visual Studio that generates the application, and it also makes available through the store asset packs that each contain the assets for a particular scale factor. Now, this MRT technology is not, as I said earlier, just about scale factors. This is a great way to manage localizable strings as well. You can have your different locales in different asset packs. And the nice thing about that is that at runtime, or at download time, when I have an app and I get it from the store basically looks at my client machine and it says something like, oh, you're English, you don't need high contrast themes because you're running in the normal theme, and you've got 150% scaling. So I'll give you any 150% assets I can find. Failing that, I'll give you 200. Failing that, I'll give you 400. Failing that, I'll give you 100. It will give you the best selection that it can find out of whatever the developer has provided, and it will download those to my machine. Now, you may ask, well, when I'm running Multimon, I've got a 100% display and a 200% display. The answer is very simple. The store detects both of those, and it sends you all of those. I hear the skeptical voices. What about if I add a display later on with a different scale factor? That's actually covered too. Let's say that I've only got a 200% asset on my machine here, and I end up connecting that to a low-density monitor, and 100% would be more appropriate. Or the other way around, which would be even more important. If I only had a 100% asset and I connected a high-density monitor, and I would really like to have a nice, crisp presentation. Well, what will happen at that instant is you'll just have your 100% asset. The system will scale that up to 400%. But it will also kind of put a check mark in there saying, whoa, you've got a 400% scale factor you could use now. And there actually is one on the store. I see it. So let me mark your application as suitable for an update. And the next time you go to update your application, which you may notice right away through the notification center, what you'll get is actually not a code update, but you'll get the new assets you need in order to have a crisper experience on that device in the future. So that's the asset pack technology. That's the technology that only 20% of our developers are using today. We really need everybody to picking up on this and taking advantage of it. So I'm going to come back to now that question of 100 and 200 and 400 and tell you what that buys you. We think 100% is definitely the starting point. It is, in fact, the default. So if you don't do something extraordinary, Visual Studio, when it goes to build your application, will say, wait, you don't have a 100% for this. And you have to actually go into the manifest and make changes if you don't want to provide a 100%. And it makes sense because 85% of our desktop devices are still running at 100% today. Even with the high DPI devices that are coming, there's a lot of legacy hardware out there, and they're still the low end, the cheapest thing you can buy out of the store. Some of the new low-end tablets are also falling into that space. Phones are not falling into that space. Phones started around 150, maybe a few at 125. But this, as you can see, is going to be a huge number of devices. Number two, I think priority is 200%, because then that gives you great downscaling coverage for high DPI desktops, which traditionally are 125, 250, 150, 200, maybe even 250. The 200 will give you pretty good results. And it also, by the same token, gives you really good coverage for most of the phones that you're likely to run on that are higher, running starting at 125 all the way up to 300%. But then we think the third one, 400%, is really important for future-proofing because we already know QHD phones are here. And the 4K tablets are coming, and they'll be down to fairly small sizes. And by the way, when you do that, it also improves some of these high-end devices that are already out there. It's better than the 200% for those. So we really think these are the three important ones to nail and get right. And by the way, if you're porting from an iOS app, you've already got these two. And if you were porting from Android, you probably have all three. That is, unless you were only delivering iOS and Android, the 100% assets. So now's the time to get out of that 56% of our developers and start providing better assets. We also have telemetry data that says about 43% of our users notice scaled up assets in use and find them ugly, not good to look at. So there's a huge number of users that you could be making quite a bit happier by providing these higher levels of assets. And this would be setting up your app for success against your competitors. And if you're reluctant to do that at first, at least keep an eye out for feedback and see if people are complaining about your visuals. And if you start to see that, take that as a sign you need to upgrade your assets. Here's an interesting table that just tells you kind of some sample examples of devices that would actually fall into these various categories and kind of a sense of how they look abstractly. I won't talk through that, but it's a good thing to sort of look at. What's kind of nice is if you stick with our 100, 200%, 400% device advice, you can see what kind of coverage you get from each one of these scale factors. Okay, so we want you to make 100, 204% assets. How do you know how big to make them? I mean, if you're going to author assets, you're probably working in some kind of a physical pixel space. You really want to you want the 200% asset, for example, to be exactly the right physical size to take up that many pixels so that it doesn't have any stretching by the runtime. And so does this mean now, even though we've sort of told you to do everything in effective pixels, you now have to worry about actual pixels? Not really. As a designer, you should still be starting with your effective pixel UI layout, because the size in effective pixels is actually the 100% physical size you need to target. So if you wanted to have a 300 by 300 effective pixel icon or a picture of some kind, then that's your 100% size. And your 200% size is going to be double that, and your 400% size quadruple that. So the math is very easy, nothing hard to worry about. You don't need to know about what the actual sizes are going to be at runtime. You just need to know, I want it to be 300 by 300 effective pixels, and then these are the sizes you need to author. I'm going to take a quick moment here to skip over and just show a quick demo in VS. I'm going to use a different machine for this. This is almost a no-brainer of an app. I basically took a new project, just opened up VS, started a new project. I went into the main panel, and you can see where the default grid was. And I just added an image, and I gave it a source name, assets sample.ping, and I moved it around a little bit till I got where I wanted it. And then over here in the assets file, you can see I've got sample.scale-100, scale-200, scale-400. So I created those offline, just using a bitmap editor, really, and I dumped them in here. And immediately, VS knows how to connect those because it's got the MRT technology built in. It's connecting them to that, and so you're seeing actually the 400% scaled asset. Now, why are we seeing the 400 here? The answer is that in my designer, I happened to pick this particular capability from the drop-down. So this would be a 5-inch phone, 1080p phone, which will default to 300% scaling. And so since I'm providing 1, 2, and 4, the best fit for 300 is going to be to downscale from 400. That's what MRT would do at runtime, and that's what VS is showing me here. And you can see very easily that if I were to switch this to, say, a 100% scale device, that it picks the 100% scaling. So it's kind of interesting, actually. You can, just as further proof that you don't need to have all these scale factors, you're at 250. I'm still using the 400. You really can't tell visually that that's being downscaled, but it is on the fly. So that's really all there is to this. It's very easy. It's almost intuitive in terms of dumping your things in, having them named appropriately, connecting them up. And again, the only connective tissue there was having the source name, assets./sample.ping. So please study this and make sure you get this into all of your applications. Just a word about asset authoring. In the demo I just showed you, I just used a bitmap editor. It was a an open source kind of thing that anybody can get their hands on. Didn't do a lot of work. In real life, of course, you probably have a higher artistic goal you're striving for with your assets. We would ask you to use vector assets whenever possible. There are a number of reasons why. They give you the highest quality artwork at any scale factor. So if you've got something that looks really good, it's probably going to look good at any scale factor you would want to spit out. And it's very easy to do that. So in fact, you may want to just go ahead and support all the scale factors at the very beginning. It gives you the most control over the way things look. And if you were to do that, you'd sort of fit into that second stage on the pyramid. It's also easy to come back to later on. You can just imagine you put out your app, it's selling well, but there's a barrier towards it in Europe because you need some localized versions, and unfortunately your artwork has some of that localized text in it. Well, if you use vector design tools, you just go back in there and you edit those strings and you spit them out, and you use MRT to organize them as both scale factor and language dependent assets, and you're done. So it's a lot easier than having to work with bitmap editors. If you are using bitmap art tooling, then our recommendation would be start with the 400% because it's a lot easier to scale that down and then crisp it up than it is to blow it up and try to crisp it up. You'll end up touching a lot more pixels if you do it the other way around. And by the way, if you're using vector design tools like Adobe Illustrator or the like, there are already all kinds of scripts out there for Android and the like that you can just use that will spit out all the scale factors you need to support. So let me sum up here. Give you kind of the call to action. We want to see assets at 100, 200, and 400% in all applications, not just 56%. We think this is the right way going forward. It'll put you in a great place to be future-proof for future devices, and it'll give you a great experience on all the existing devices. We also want you to use those asset packs because it's really important to be taking up a minimal footprint, especially on the lower-end devices. It's easy to do, and only 20% of you are using that now. So learn more about that. That will take care of all the asset work. Then the bigger thing is go off and attend some of these other talks because we're going to spend a lot of time talking about, now that we're doing the scaling for you and we're giving you these effective pixels and these effective resolutions, how do you do your layout? How do you handle changes in effective resolution as an application moves from one display to another or is deployed on different devices? And there's a whole set of talks here with different levels of detail about this. Some are very high level, some are very design focused, but I think they're all excellent, and there's a lot more information on all of that there. So that's what we're asking for. Take off this big bite with the effective resolution and effective pixel work, and take a step up here in the bitmap area so that we're getting a better experience for all of our customers. All right. Well, thanks very much. I hope this was helpful to you, and look forward to seeing you again.